inference for a population proportion. When performing a test of significance about a population proportion, we will use a one proportion z-test. For these inferences, P naught, P sub 0, represents the claimed population proportion. Our null and alternate hypothesis will be H naught is P is equal to our claimed population proportion, and HA will be P compared to the claimed population proportion with a not equals, less than, or greater than. The conditions that we need to meet for a population proportion test: the sample must be a simple random sample from the population of interest. The population must be at least 10 times the size of the sample. The number of successes and the number of failures must each be at least 10. In other words, n times p needs to be greater than or equal to 10, and n times 1 minus p, our failure rate, must be greater than or equal to 10. Recall that our statistic used for proportions is p hat, which is equal to our number of successes divided by our number of observations. For tests involving proportions that meet the above conditions, we use the z-test statistic, where z is p hat minus p naught divided by the square root of p naught times 1 minus p naught over n. Z is the only test statistic we will be using with proportions. For example, a new shampoo is being test marketed. A large number of 16-ounce bottles were mailed out at random to potential customers in hope that the customers will return a questionnaire. Out of the 1,000 return questionnaires, 575 indicated they liked the shampoo and will consider buying it when it becomes available on the market. We want to perform a hypothesis test to determine if the potential customers is more than 50%. Now, we're not given a significance level, so we choose alpha to be 0.05. Since our population would be all people that this is marketed to, 1,000 is less than 10 times the population. Our population proportion, p hat, will be 575 divided by 1,000, or 0.575. And since our p naught is 50%, n times p naught and n times 1 minus p naught, they're both greater than 10. So our null hypothesis is that p is equal to the claimed population proportion, which is 0.5. HA uses these same values, but we need to determine the inequality that goes between them. We want to know if it's more than 50%, so we use a greater than. Let's draw our rejection region. Draw a normal curve. We will shade the right tail since it's a greater than. Alpha equals 0.05 means the shaded area is 0.05. So since we're using a z-test statistic, we'll do inverse norm of 0.95, which is 1 minus 0.05, to get a critical value of 1.645. Our test statistic is the z-value of our p hat minus our p naught divided by the square root of p naught times 1 minus p naught over our n. This comes out to be 4.743. If I graph this value within this rejection region, it would be very far to the right and in the shaded region. So we can see that we will be rejecting the null. We'll verify that with our p-value, which is the probability that z is, again, use the symbol that we have in our alternate, and then our test statistic goes here. This is a normal distribution, so we'd use normal CDF or p-norm to compute this probability, and it's 0.0000105, which is definitely less than our alpha of 0.05. So in this case, we will be rejecting the null hypothesis. Our conclusion statement would say that we have overwhelming evidence to reject our null hypothesis, which states the population proportion is 50%, and conclude that the proportion of potential customers is more than 50%. Next example. Mars claims that they produced M&Ms with the following distribution. A bag of M&Ms was randomly selected and the color counts are given in this chart. We want to conduct an appropriate test the manufacturers claim just with the proportion of brown M&Ms. Well, there's 14 brown M&Ms. And if I count up all the values in this chart, we have 56 M&Ms total. So our p hat, our proportion for the sample, is 14 out of 56, or 0.25. We will assume that there are many M&Ms out on the market, so 56 is definitely less than 10 times our population. 10 times 56 is definitely less than our population here. We have a simple random sample, our bag of M&Ms. So let's state our null and alternate hypothesis. So we write our population proportion for the browns, which is 30, and our null is always in equals. And then we want to decide whether we have a less than, greater than, or not equals to. We just want to test the claim that they have that amount of brown M&Ms. So we want to see if it's different. Our rejection region would be graphed with a two-tailed test since we have a not equals. So we're going to shade two tails of our normal distribution. We're not given an alpha, so let's choose alpha equals 0.05. Since it's two-tailed, each tail is half of that. So I'm going to do inverse norm of 0.025, which gives negative 1.96, or I could do inverse norm of 0.975 to get the positive. These two, again, are equal in absolute value. Remember, this curve centered around 0. Our test statistic is 0.25 minus 0.3 divided by the square root of 0.3 times 1 minus 0.3 divided by our n, which is 56. This comes out to be negative 8.816. When I graph this value on my rejection region, we can see that it does not fall in our shaded region, so we will be failing to reject. Our p-value should verify this. Now, our probability, since it's two-tailed, is a double. Remember, it's either this or that, so we're going to do twice the probability that z is, since this is a negative, I'm going to say less than. If it were a greater than, I'd use if it were a positive, I would use a greater than. So 2 times our normal CDF for this value would give me 0.4145, which is definitely greater than our alpha. So we will fail to reject our null hypothesis, which states that the population proportion of brown M&Ms is 30%.